Somewhere in a defense lab in the United States, there is a box the size of a shoebox that just quietly made GPS obsolete. It does not look dangerous. It does not look revolutionary. It looks like something you would toss in a closet and forget about. But inside that box is a piece of technology so precise that it will only lose 1 second of accuracy every 30 million years. Let that sink in for a moment. 30 million years. That is longer than humans have existed on this planet. And the United States military just put this device into production. This is not a prototype anymore. This is not a lab experiment stuck behind glass. This is a real, working, mass-producible quantum clock, and it is about to change how wars are fought, how ships sail, how planes fly, and how missiles find their targets. If you have ever used Google Maps, if you have ever tracked a delivery, if you have ever trusted a blue dot on a screen to tell you exactly where you are, you have depended on GPS without even thinking about it. But GPS has a secret weakness, one that has been quietly exploited for years by hostile nations, and the Pentagon just found a way to make that weakness irrelevant. Stick around, because what you are about to hear sounds like science fiction, but it is happening right now in 2026, and almost nobody outside of defense circles is talking about it. Let's start with the problem, because you cannot understand why this shoebox matters until you understand how fragile the system underneath your phone actually is. GPS, the Global Positioning System, was built by the United States military decades ago. It works because a network of satellites orbiting the Earth constantly broadcasts extremely precise time signals. Your phone, your car, your plane, your ship, all of them listen to those signals from multiple satellites at once. By comparing the tiny differences in when each signal arrives, your device calculates exactly where you are. This sounds simple, but it depends entirely on timing accuracy down to billionths of a second. A timing error of just a few nanoseconds can shift your calculated position by a meter or more. Now imagine that error scaled up during a missile strike, a naval maneuver, or a fighter jet landing in bad weather. Suddenly a tiny timing glitch becomes a matter of life and death. Here is the part that should genuinely worry you. GPS signals are incredibly weak by the time they reach Earth. They travel over 20,000 kilometers from space, and by the time they arrive, the signal strength is roughly comparable to a light bulb viewed from thousands of miles away. That means GPS signals are shockingly easy to drown out. A cheap jamming device, sometimes costing less than a few $100s, can overpower a satellite signal within a local area. This is called jamming, and it simply blocks GPS from working at all. But there is something even sneakier than jamming, and it is called spoofing. Spoofing does not block the signal. It replaces it. A hostile actor broadcasts fake GPS signals that look completely legitimate to your receiver. Your device thinks it is getting real satellite data, but it is actually being fed false coordinates. The terrifying part is that spoofing does not throw an error message. Your navigation screen looks perfectly normal. It just tells you the wrong location with total confidence, while you have no idea anything is wrong. This is not some hypothetical, theoretical risk. It is already happening at a massive scale. According to aviation industry data released in 2025, GPS spoofing incidents affecting commercial aircraft nearly tripled between 2023 and 2025. Jamming incidents rose by 67% over that same period. Pilots flying through parts of Eastern Europe, the Middle East, and areas near the Black Sea have reported their navigation systems suddenly showing them in completely wrong locations, sometimes hundreds of kilometers off course, without any warning at all. In one widely reported case, the plane, carrying a major European political leader, was unable to land for over an hour because of suspected jamming near a conflict zone. If a head of state's aircraft can be blinded like that, imagine what it means for a soldier on the ground, a warship in contested waters, or a cargo plane full of civilians. The maritime world has it just as bad, maybe worse. Between August 2023 and April 2024, roughly 46,000 GPS interference incidents were recorded over the Baltic Sea alone, an area that has earned the grim nickback of being the Bermuda Triangle of GPS, due to how frequently ships and aircraft lose accurate positioning there. In the waters near the Strait of Hormuz, one of the most critical shipping corridors on Earth, jamming clusters have exploded in number, disrupting the automatic identification systems that vessels rely on to avoid collisions. During periods of heightened conflict in the Middle East, maritime intelligence firms reported that daily GPS interference incidents nearly doubled within just a few weeks, jumping from a few hundred a day to well over 600. Ships were showing up on tracking systems and locations they were never actually in. Sailors were essentially flying blind in some of the busiest waterways on the planet. Now here is the strategic nightmare buried inside all of this. The United States military depends on GPS for almost everything. Precision-guided missiles use GPS timing to hit their targets within centimeters. Fighter jets use it for navigation in contested airspace. Naval fleets use it to coordinate movements across oceans. Communication networks use GPS timing signals to keep everything synchronized, because without precise, shared timing, encrypted communications and radar systems fall out of sync and stop working properly. If an adversary can jam or spoof GPS across a battlefield, they do not need to shoot down a single plane or sink a single ship. They just need to blind the entire force's sense of time and space. This is exactly the kind of vulnerability that modern militaries like Russia have been exploiting for years, using powerful jamming systems to protect sensitive airspace and disrupt enemy drones. And it works. It works well. Which is exactly why the Pentagon decided GPS alone could no longer be trusted as the backbone of modern warfare. This is where DARPA enters the picture. DARPA, the Defense Advanced Research Projects Agency, is the same organization that helped create the internet, GPS itself, stealth technology, and touchscreen interfaces. When DARPA identifies a national security gap, they do not just study it, they fund an entire pipeline to solve it. And for the last several years, DARPA has been running a program with a strangely casual name for something this important. It is called ROCKAN, short for Robust Optical Clock Network. The mission of ROCKAN is simple to state, but incredibly difficult to achieve. Build a way to keep military-grade timing precision even when GPS is completely jammed, spoofed, or knocked out entirely. Not for a few seconds, not for a few minutes, for weeks, or even months, without ever touching a satellite signal. The way ROCKAN solves this problem is through something called an optical atomic clock. To understand why this matters, you need to understand how normal GPS timing actually works in the first place. GPS satellites use rubidium-based atomic clocks. These clocks measure time by observing the resonant frequency of rubidium atoms exposed to microwave radiation. Atomic clocks have been around since the 1950s, and they are remarkably accurate compared to any mechanical clock. But optical atomic clocks are an entirely different level of precision. Instead of using microwave frequencies, optical clocks measure atomic transitions using light frequencies, which oscillate far faster than microwaves. That higher frequency means far more precise timekeeping, similar to how a ruler with thousands of tiny tick marks lets you measure something more precisely than a ruler with only 10 marks on it. Optical atomic clocks are, quite simply, some of the most accurate timekeeping devices ever built by humans. The problem is that optical atomic clocks have traditionally been enormous, delicate, and only usable inside climate-controlled laboratories. We are talking about room-sized setups full of lasers, vacuum chambers, and vibration-sensitive optics that could never survive being bolted onto a fighter jet or dropped onto a battlefield. This is the exact bottleneck DARPA set out to destroy. According to DARPA's own program manager overseeing this manufacturing effort, nobody had ever successfully scaled quantum manufacturing before because integrating and miniaturizing components like advanced lasers and photonics is exceptionally difficult even for a single prototype, let alone at industrial scale. Solving that bottleneck, in his own words, was a DARPA-level problem. And now, according to the agency's most recent updates, they have actually solved it. DARPA's ROCKAN program is developing two distinct classes of these optical clocks. The first is the one everyone is talking about, the shoebox-sized unit. This compact clock is designed to be small enough for airborne and spaceborne platforms, yet it can hold GPS-level timing precision, meaning sub-nanosecond accuracy, for up to 2 weeks without ever syncing to a satellite. And, remarkably, it consumes about as much power as a household light bulb. Think about that for a second. A device with the timing precision that once required an entire research laboratory now fits in a shoebox and sips power like something you would screw into a lamp. The second class is a larger unit, roughly the size of a washing machine, designed to act as a regional master clock. This larger version can maintain GPS-level precision for more than 6 months without any resynchronization at all. Picture a mobile command post or a naval base able to run precision-guided systems for half a year straight, completely immune to enemy jamming because it never needed GPS in the first place. This is not just a defense concept sitting on a whiteboard anymore. DARPA has already selected a private company, IonQ, to build the actual manufacturing pipeline for these clocks. IonQ, a quantum computing company that acquired a smaller quantum sensing firm called Vector Atomic back in 2025, has produced a working device called the Evergreen O5. This clock fits inside a container of roughly 5 liters, about the size of a shoebox, yet it delivers timing stability of 50 femtoseconds at 1 second, and it can hold nanosecond level accuracy across a 10-day holdover period without touching GPS at all. IonQ says that level of precision translates to losing less than 1 second of accuracy over 30 million years. To put that size advantage into perspective, this device occupies only about 1/75th the volume of the active hydrogen masers that were previously used for similar precision tasks. That is an almost unbelievable leap in miniaturization. And it is exactly the kind of leap that turns a laboratory curiosity into something you can actually deploy on land, at sea, or in the air. And this is not some small side project buried in a Pentagon budget line either. DARPA has backed this Evergreen 05 program with a $28 million contract extension, along with an additional unexecuted $30 million option sitting on the table. That is real money, committed specifically because this technology has already passed extensive testing in national labs and out in the field. According to reporting on the program, DARPA expects a full manufacturing facility for these optical clocks to open within the next year, with deliverable products ready for integration into various Department of Defense platforms within a year after that facility opens. In other words, this is not a someday maybe technology anymore. This is a scheduled, funded, actively in progress manufacturing rollout. The Shoebox clock is not coming. It is already being built. Now, before you assume this technology just appeared out of nowhere in 2026, understand that this has been years in the making. Back in 2022, DARPA-backed optical clock prototypes were successfully field tested during a major military exercise where 3 shoebox-sized rack-mounted clock units were tested in real operational conditions rather than a clean laboratory. That successful field demonstration is a big part of why the Pentagon felt confident enough to commit tens of millions of dollars toward full-scale production years later. This program did not rush from concept to deployment overnight. It has been slowly, methodically proven at every stage, which is exactly the kind of validation that separates a real military capability from an experimental gimmick that never leaves the lab. But timing precision is only half of the bigger quantum navigation story. DARPA has also been funding related programs focused on quantum navigation itself, not just quantum timekeeping. One notable example involves an Australian quantum technology company called Q2Troll, which received DARPA contracts worth over $24 million to build next-generation quantum navigation systems for aircraft, ships, and ground vehicles. This is a parallel but connected effort to eventually replace not just GPS timing, but GPS positioning itself using quantum sensing hardware that does not rely on satellites at all. Researchers have even discussed the eventual possibility of a shoebox-sized quantum inertial measurement unit, essentially a self-contained sensor that uses quantum-level precision in accelerometers and gyroscopes to track position and movement without ever needing an external signal. We are not fully there yet with that particular piece of the puzzle, but defense researchers say it is well within the realm of known physics. And defense analysts project the broader quantum navigation industry could be worth between $3 and $5 billion by the year 2030. So why does all of this actually matter to you, sitting there watching this video, someone who has probably never worn a military uniform and never will? Because technology born inside defense labs almost always trickles down into civilian life eventually. GPS itself was originally a military-only project before it became the thing guiding your Uber driver and your food delivery app. The internet was a defense research project before it became the platform you're using to watch this very video right now. Touchscreen technology, voice assistants, even the basic architecture of modern computing, all of it has roots in defense-funded research that eventually became consumer technology. If quantum clocks and quantum navigation prove successful at a military scale, the next logical step is miniaturizing and cost-reducing them for commercial aviation, commercial shipping, autonomous vehicles, and eventually even the smartphones sitting in your pocket. Imagine a future where your phone's location never gets fooled by a cheap $200 spoofing device because it is not relying on a satellite signal that can be jammed in the first place. That future starts with programs exactly like this one. There's also a deeper story here about why the timing of this breakthrough matters so much geopolitically. We are living through a period where GPS interference has become an actual weapon of modern warfare, used deliberately and repeatedly by hostile actors to disrupt everything from commercial shipping lanes to civilian aircraft. Multiple recent reports have described a dramatic surge in jamming attacks targeting both GPS and broader satellite communications, with new interference clusters appearing across contested waters in the Middle East and Eastern Europe. Analysts have warned that these disruptions are not isolated incidents anymore. They represent a new and increasingly normalized form of electronic warfare, one that blurs the line between military conflict and civilian disruption. Because a jammed GPS signal does not care whether it is confusing a warship or a passenger jet full of tourists. When your entire global economy, from container ships to airline schedules to financial transaction, timestamps quietly depends on GPS timing signals working correctly, an enemy that can reliably disrupt those signals holds a genuinely terrifying kind of leverage. Quantum clocks are the United States military's answer to taking that leverage away entirely. Now let's talk about the actual physics for a moment, because it is genuinely fascinating once you break it down simply. A rubidium atomic clock, the kind used in current GPS satellites, works by exposing rubidium gas to microwave radiation tuned to a very specific frequency that matches an energy transition inside the atom. When the microwave frequency exactly matches that transition, the atoms absorb energy in a highly predictable, extremely stable pattern. Engineers use that predictable pattern as an incredibly precise pendulum, essentially a heartbeat that never skips a beat, and that heartbeat becomes the foundation for GPS timing. Optical atomic clocks do the same fundamental thing, but using light instead of microwaves. Because visible light oscillates at a much higher frequency than microwaves, roughly 100,000 times higher, an optical clock can divide time into far smaller, far more precise increments. It is the difference between measuring distance with a ruler marked in centimeters versus a ruler marked in micrometers. Both are technically rulers, but one gives you dramatically more precision for the exact same length of material. The real engineering miracle here is not the physics of optical clocks themselves, since scientists have understood this concept for years. The miracle is making that physics survive outside a laboratory. A laboratory-grade optical clock typically needs an isolated, vibration-free, temperature-controlled room, delicate laser systems, and constant expert calibration. None of that works on a fighter jet pulling 9 Gs, on a warship rocking in rough seas, or on a forward operating base in a desert with sand, heat, and constant vibration from nearby equipment. Ruggedizing this technology, meaning making it durable enough to survive real-world military conditions without losing its extraordinary precision, is genuinely one of the hardest engineering challenges in modern defense technology. That is precisely why DARPA's program manager called this a DARPA-level problem in the first place. It required not just brilliant physicists, but brilliant mechanical and photonics engineers working together to shrink a laboratory into a shoebox without breaking the delicate quantum processes happening inside it. If you're enjoying this deep dive into one of the most under-the-radar defense stories of the year, do me a favor and hit that like button. And if you haven't already, go ahead and subscribe, because there is a lot more of this kind of cutting-edge defense and science coverage coming. Let's also talk about what this means for the average soldier on the ground, because that is ultimately who this technology protects first. Imagine a special forces unit operating deep inside contested territory, far from any friendly communication network, where an adversary is actively jamming every GPS signal in the region to prevent coordinated strikes. Under current systems, the unit's precision-guided weapons become significantly less accurate, their navigation becomes unreliable, and their ability to coordinate with air support or other units becomes dangerously compromised. Now imagine that same unit carrying equipment powered by a shoebox-sized quantum clock that has already been holding perfect GPS-level timing for the past week, completely independent of any satellite signal. Their weapons stay precise, their coordination stays intact, their sense of location and timing simply does not degrade, no matter how aggressively the enemy tries to jam the airwaves around them. That is the actual battlefield difference this technology creates, and it is not a small one. It is potentially the difference between mission success and mission failure, and in the worst cases, the difference between life and death for the people carrying that equipment. It is also worth mentioning how this fits into a much larger quantum technology race that most people are not paying attention to. Quantum sensing is not just about clocks. DARPA has openly stated that this manufacturing breakthrough is intended to extend beyond timekeeping into quantum radio frequency sensors, infrared imaging systems, and other quantum-adjacent technologies. The underlying challenge across all of these fields is the exact same one that Rocky N just solved for optical clocks, taking delicate, laboratory-only quantum hardware and making it rugged enough for real-world deployment at meaningful scale. If DARPA and IonQ have genuinely cracked that manufacturing bottleneck for clocks, the same lessons and the same production, techniques can likely be applied to an entire family of quantum sensors, which means this shoebox clock might just be the first domino in a much bigger wave of quantum defense technology hitting production over the next several years. There is an important financial and industrial angle to this story, too, one that deserves attention beyond just the pure science. IonQ is a publicly traded company, and analysts have pointed out that this DARPA contract represents something the entire quantum computing industry has been waiting years for, a genuinely practical, revenue-generating, real-world application of quantum technology outside of pure research. For years, quantum computing has been criticized as a field full of promising theory, but very little practical commercial payoff. A defense contract worth tens of millions of dollars, tied to an actual physical product being manufactured and delivered to the Department of Defense, is a meaningful signal that quantum technology is finally crossing over from experimental science into deployable, purchasable hardware. That shift matters not just for defense contractors, but for the entire trajectory of the quantum technology industry as investors and governments look for evidence that quantum research can eventually translate into products people and militaries actually use. Let's zoom out for a second and think about the bigger picture here, because this story is really about something larger than one clock or one contract. For decades, the United States built an enormous strategic advantage around GPS, a system so dominant and so trusted that the entire global economy quietly reorganized itself around it. Shipping, aviation, agriculture, banking timestamps, cell, phone networks, power grid synchronization, all of it leans on GPS timing signals working correctly every single second of every single day. That dominance became a vulnerability the moment adversaries figured out how cheaply and effectively they could disrupt it. What DARPA and IonQ are building with this shoebox-sized quantum clock is essentially an insurance policy against that vulnerability, a way to keep the machinery of modern military operations and eventually modern civilian life running smoothly even when the sky above you is filled with hostile jamming signals. It is not just a defense upgrade, it is a fundamental hedge against one of the most exploitable weaknesses in the entire modern technological world. Of course, this technology is not perfect, and it is worth being honest about its current limitations rather than overselling it as some flawless silver bullet. The shoebox-sized clock currently holds GPS-level precision for about 2 weeks before it would need resynchronization, and the larger washing machine-sized master clock can hold that precision for roughly 6 months. That means these systems are not yet a permanent, indefinite replacement for GPS. They are, more accurately, an extremely powerful holdover system, something that keeps critical operations running with full precision during the exact windows when GPS is jammed, spoofed, or simply unavailable. For most military scenarios, that is more than enough, since jamming attacks tend to be localized and temporary rather than permanent global blackouts. But it does mean GPS itself is not being fully replaced or shut down. It is being backed up by a far more resilient, far more trustworthy alternative that can carry critical systems through exactly the moments when GPS becomes a liability instead of an asset. Another honest limitation worth mentioning is cost and scale. Building a manufacturing pipeline capable of producing these clocks in meaningful quantities is still a work in progress, with DARPA expecting the actual production facility to open within the coming year, and deliverable products following roughly a year after that. This is fast by defense industry standards, where new technologies often take a decade or more to move from concept to deployment, but it is not instantaneous. It will likely be several years before these quantum clocks are widely distributed across military platforms, and even longer before any version of this technology becomes affordable enough for civilian or commercial use. Still, the trajectory here is remarkably clear. The core scientific and engineering problems that once made this technology impossible outside a laboratory have been solved, tested in the field, and are now actively being scaled into real production. That is an enormous milestone, even if full deployment takes a few more years to fully materialize. It also helps to understand just how much money and infrastructure the world has already built on top of the assumption that GPS will always be there and always be accurate. Airlines schedule flight paths around it. Banks timestamp financial transactions. Using it, power grids synchronize massive electrical systems using it. Farmers guide automated tractors across fields using it. Even cell phone towers rely on precise timing signals to keep your calls from dropping and your data from scrambling. When you start adding up every single industry quietly leaning on the exact same vulnerable system, you begin to realize just how enormous the stakes actually are. This is not just a story about fighter jets and warships. It is a story about the invisible infrastructure holding up nearly everything in modern life, and about what happens when a handful of hostile actors figure out how cheaply that infrastructure can be disrupted. A shoebox-sized clock might sound like a small niche military upgrade, but the ripple effects of solving this vulnerability reach into nearly every corner of the global economy. It is also worth pointing out how unusual it is for a story this significant to stay so quiet in mainstream coverage. Most viral tech stories involve something flashy: a new smartphone, a new electric car, a new artificial intelligence chatbot doing something unexpected. A precision clock does not photograph well. It does not have a dramatic launch event with bright stage lighting. It does not come with a celebrity spokesperson. But history tends to remember quiet breakthroughs like this one far more than the flashy ones, because quiet breakthroughs are usually the ones that actually reshape how the world works behind the scenes. GPS itself was once an obscure military project that almost nobody outside of defense circles cared about, right up until the moment it became the invisible backbone of global navigation for billions of people. This quantum clock story has exactly that same quiet, unassuming energy right now, and that is precisely why it deserves more attention than it is currently getting. There's also a competitive angle worth understanding, because the United States is not the only nation racing toward this kind of technology. Other major powers, including China and Russia, have their own quantum research programs actively exploring precision timing and quantum sensing for military applications. Whoever manages to fully solve the miniaturization and ruggedization problem first gains a meaningful strategic advantage, not just in raw military capability, but in the broader technological race that increasingly defines global power in the 21st century. This is part of why DARPA moved as aggressively as it did, committing tens of millions of dollars specifically to solve the manufacturing bottleneck rather than leaving the technology stuck at the prototype stage indefinitely. Being first to develop a working quantum clock in a laboratory means very little strategically if you cannot actually manufacture and deploy it at scale before your rivals catch up. That is exactly why the shift from prototype to production line matters so much, and it is exactly why this story is being treated with such urgency. Inside defense circles, even though most of the public has never heard about it, consider also how this connects to the drone warfare revolution that has reshaped modern conflict over the past several years. Small, cheap, GPS-guided drones have become one of the defining weapons of contemporary battlefields, used extensively in recent conflicts to strike targets with remarkable precision at a fraction of the cost of traditional guided missiles. But that entire drone warfare strategy depends heavily on reliable GPS signals, reaching the drone throughout its flight path. Jam that signal, and a multi-$1,000 precision drone can become a confused, wandering piece of expensive scrap metal within seconds. Militaries on both sides of recent conflicts have leaned heavily into jamming, specifically because it is such an effective, low-cost way to neutralize an entire category of modern weaponry. A resilient timing source that does not depend on GPS at all fundamentally changes that calculation, potentially restoring precision guidance capability to drones and missiles even in heavily jammed environments, which is exactly the kind of capability shift that keeps defense planners awake at night thinking about what their adversaries might be building next. So where does this leave us? The United States military just quietly solved one of the most dangerous vulnerabilities in modern warfare, the fragile dependence on satellite signals that can be jammed or faked by anyone with a cheap enough transmitter. They did it not with some flashy new weapon or a massive visible show of force, but with something almost boringly simple sounding, a really, really good clock. A clock so precise it will barely lose a single second over 30 million years, small enough to fit in a shoebox, cheap enough in power draw to run off something comparable to a household light bulb, and rugged enough to survive combat conditions in the field. It is easy to overlook a story like this because there is no explosion, no dramatic unveiling, no flashy press conference. It is just a quiet, methodical engineering breakthrough happening in defense labs and manufacturing facilities across the country. But make no mistake, this is one of the most consequential pieces of defense technology to reach production in years because it strikes directly at the vulnerability adversaries have been exploiting with growing confidence and growing frequency. The next time you glance at a map app on your phone and trust that little blue dot without even thinking twice about it, remember that the system behind it has a real exploitable weakness, one that has already disrupted commercial flights, confused massive cargo ships, and even forced a world leader's plane to circle helplessly for over an hour. And remember that somewhere in a defense facility right now, engineers have built the answer to that weakness, and it fits in a box the size of the one your last pair of sneakers came in. Technology like this rarely stays confined to military use forever. Give it enough years, and do not be surprised if some version of this exact quantum clock ends up quietly powering the navigation system in your car, your phone, or the plane you fly on for vacation. The shoebox that just replaced GPS might be the most important piece of hardware you have never heard of until now. If this kind of deep dive into the technology quietly shaping global power is something you want more of, make sure you like this video and subscribe to the channel so you never miss the next one, because stories like this one are exactly what this channel is built around, and there are a lot more of them coming.